Good morning, ladies and gentlemen. This is Ben Keyser with Applied Flow Technology, and I want to thank each and every one of you for joining in with us today on the webinar. And it's great to have you all, and I hope that you all are doing well. If you can hear me loud and clear on your side with the GoToMeeting, please click on the raise hand button to give me a high five to let me know that you can hear me. And I'm starting to see some high fives coming in. That's looking good. Awesome. Well, I'm glad that you all can hear me. Thanks again. And I hope everyone's having a good week. And I'm excited to present our webinar today to you on cavitation modeling. So we're going to get deep into the weeds here very soon. And before that, I want to point out something. Did you know that Applied Flow Technology has a sister company that does consulting services? Well, in case you didn't know, we do. And so you can actually get to that information by going to the website aft.com. AFT.com should be a really easy website to remember. So once you get there, if you go to the support menu and then come down to consulting, there's a couple different options. There's a block of hours that you can purchase off the shelf through AFT. One of our support engineers will be able to help you. But if you need something more in depth on your project, where you need us to build a model of your system and do more of the analysis for you, maybe you're crunched for time. Maybe you don't have the in-house expertise right away. Maybe you want to, or maybe you are flooded with other projects to where you need to farm something out to be able to get your client a good solid answer. This is where our sister company, Purple Mountain Technology Group, is of incredible value to you. And so, this also saves from, if you don't have the expertise, rather than having to send somebody out for training on our software, hire Purple Mountain, and Purple Mountain will be able to assist you. So if you click on Learn More for Purple Mountain, this will take you to the Purple Mountain Technology Group website, and this is where you'll be able to see what types of services that we offer: steady state fluid modeling, Waterhammer and transient analysis, etc. We have a very vast amount of experience in multiple industries and all sorts of applications, to where we will be able to help you very well with your work. So please visit our page, Purple Mountain Technology Group. It's pmtechgroup.com, and we'll be able to help you. And so with that here, this just gives you a picture of all the different ways that we can help. And so I want to pause really quick here. You can find my contact information. I am still with Applied Flow Technology, been with AFT for coming up on 12 years, but I also am a part of Purple Mountain Technology Group. And for PMTG, I'm the project manager and senior consulting engineer. So if you need some help with any of your projects, by all means, please reach out to me, Ben Keyser at pmtechgroup.com. That's BENKEISER at pmtech, that's TECH group.com, and I'll be glad to help. All right, so with that, I'm going to go ahead and get started, and we're going to jump into the black art modeling of cavitation. So hold on to your seats, everyone. It's going to get wild up in here. All right. So what is cavitation? Basically, it's just a phenomenon when the pressure in your piping system reaches the saturation pressure. Once that happens, bubbles start to form, and you can start to get situations where it's like balloons popping inside of your pipes. Definitely not a good situation to have. So essentially, the liquid is boiling due to low pressures rather than high temperatures. So when we take you back to your good old thermodynamic charts for your saturation pressure versus temperature, here we've got the boiling point of water at 100 degrees Celsius at 1 atmosphere. Well, if you drop the pressure down to 0.2 along the saturation line, you will be boiling even at 60 degrees Celsius. So when you're dealing with a Waterhammer or a transient situation, high pressures are not the only thing to be concerned about. Low pressures can be just as bad, if not worse, because when you start cavitating and it causes vapor volumes to form in your system, that's going to be a real issue. I'm going to see if I can hide my taskbar here. There we go. Make sure it pops up when I. Okay. So cavitation can happen in lots of situations. If you have a valve closure event, when your valve slams shut, you're going to have a high pressure wave that reflects from the valve upstream at a high pressure surge, and then as it comes back to reflect off the valve a second time, then it's kind of a low pressure reflection. And that low pressure reflection will often drop down to vapor pressure. And then on the downstream side of the valve, it very quickly will drop to vapor pressure. And so you're going to be cavitating on the downstream side of the valve significantly. So this is one of the key situations to watch out for when it comes to dealing with cavitation. Other times is if you have a pump trip event, well, when your system pressures just drop because there's no more energy being added to your fluid, that will very quickly be able to have the possibility to encounter cavitating behavior. You can potentially see cavitation happening on your pump impellers. That would be more so if you have MPSH problems. So if your MPSH available is not high enough than that which is required by your pump, then you're going to be cavitating inside your pump, and that's a bad situation. You're also very likely to encounter cavitation at high elevation points. So you want to make sure you check your high elevation areas in transient analysis to make sure your pressures are above vapor pressure. So these are just some of the examples and situations where you can run into cavitating behavior in your system. So what does this vapor cavity formation and collapse look like? It's essentially a two-stage process. So first off, you're going to be in a situation where once the pressure reaches vapor pressure in your fluid, your vapor cavities are going to start growing. So your bubbles get larger and larger and larger the longer that your system is at vapor pressure. The second step is that vapor volume is going to begin to decay, and then eventually it'll collapse, and that's where it pops, and it can cause a really large pressure surge in your system. So this is just a good little picture example to demonstrate how your vapor volumes are growing, and then they're contracting, and then once the vapor volume reaches zero volume, that's basically when your volume pops, and it's going to lead to a high pressure spike. Now, a couple of terms that are important here is transient cavitation and the implications of what this sometimes might be meaning. So when we talk about transient cavitation, there's also cavitation that can be happening in typical steady state operation. So this is where you don't have a particular event like a valve closure or a pump trip that causes the cavitation. This is something where your cavitation is much more sustained over a long period of time potentially. So as I hinted at earlier, you can have cavitation inside your pump impeller. This would be if you have MPSH problems. If you got to make sure you compare your MPSH available to that which is required, and you want to make sure that you have really good margins. So check your low liquid levels situations in your reservoirs and things like that. So that's one example of cavitation that would happen in steady state, and that will destroy your impeller over time pretty quickly. You can also have cavitation through a throttled valve where you have a really large pressure drop and it's just choking off the flow. You can have cavitation if you're dealing with heat transfer. So when you go through a heat exchanger, if that heat exchanger heats things up too much and your temperatures have gone above the saturation line, then you're boiling, and that's also cavitation as well. So really important to point out, these are actually more of a two-phase flow type situation. And so when we're talking about modeling transient cavitation, like with AFT Impulse, these three things, they're not going to be modeled in that situation because these would represent more of a sustained two-phase flow phenomenon. So when we talk about a transient system, such as a valve closure, you're going to have pressure wave propagation throughout your system. And when those transient waves are causing areas of your system to reach the vapor pressure on a low pressure reflection, then that's where you're going to start cavitating. And when you have cavitation happening, then that can interrupt the liquid column in the piping. Sometimes this is called column separation. So if the cavitation grows so much where the vapor bubble fills up the entire cross section of the pipe, then that would be called column separation. So oftentimes we'll be asked, can AFT Impulse model liquid column separation? The answer is yes, to a certain extent, because column separation is wrapped up under the umbrella of just a more generalized term called transient cavitation. And then overall, when the vapor bubbles collapse, that's what's going to generate significant pressure waves throughout your system. So here are some impacts of what happens when you're cavitating. It's going to generate high pressure events, and these high pressure events can cause, well, this is an example of cavitation on a pump impeller, so this is not really always something that's caused by a transient event like a pump trip or a valve closure, but you can clearly see the damage on the pump due to the pitting here. Other situations, as your high pressure waves pass through the system, it can cause dangerous transient forces, and it can also destroy pipes and equipment. So definitely something that you want to avoid for sure. Now, how is cavitation dealt with in AFT Impulse? In AFT Impulse, we're using the method of characteristics to solve the transient mass and momentum balance equations within the software. And I'm not going to go through all that detail right now, but one of the really important things to keep in mind is that a fundamental assumption of the method of characteristics is that pipes are 100% liquid full, okay? So this is not necessarily a limitation of AFT Impulse. No, it's a limitation of the actual mathematical model itself that is used in AFT Impulse. So the reason why pipes are assumed to be 100% liquid full is because the method of characteristics assumes a constant wave speed. And when you have cavitation in your piping system, the cavitation and the vapor bubbles in your piping system, that will inherently change the wave speed of the fluid. Well, the method of characteristics assumes a constant wave speed. So as that wave speed changes in reality, cavitating behavior becomes very, very difficult to predict. So when the cavitation breaks this assumption, this is where Impulse has the model to be able to mainly model limited amounts of cavitation. So as long as the cavitation is relatively short-lived, not widespread throughout your system, and not long-lasting, where it just keeps cavitating, 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 and never stops, then Impulse is going to be pretty good to be able to determine what the first few pressure spikes are going to be when you have vapor bubble collapse. Okay, and we're going to see that here when we start looking at some examples. All right. So the way that Impulse accounts for limited transient cavitation is, this is something to remember, is that the vapor formation that's happening inside the pipe, this is staying local to each computation station in the system. Now, this webinar is not a deep dive of the basics of Waterhammer and how it's dealt with. We have several resources that describe Waterhammer in general and what pipe sectioning means and what pipe stations are. But essentially, a computation station is a mathematical point along a pipeline or along a pipe where your transient pressures, flow rates, velocities are being calculated. And so when vapor bubbles start to form, we are assuming that the vapor bubbles are staying local to each computation station. So here we have a valve, and let's say that the situation is where the valve closes and downstream we start to see cavitation. Well, when that valve closes, this section of pipe is going to be evacuated first as the liquid momentum carries on down the pipe. It's going to pull a vacuum in this section of piping, and that's going to start a vapor volume growing inside the pipe. Well, mathematically, we are assuming that the vapor volume is local to this computation station, which is at the inlet of the pipe. And then maybe we have a little bit of vapor volume in this section right here. Well, that section volume is calculated at this station. And then in this station, you have a little bit less vapor volume, and that's going to be captured at this computation station. And then down the rest of them, there's no more cavitation that's happening. So keep in mind, when you're dealing with AFT Impulse and you see cavitating behavior, those vapor volumes are local to the computation stations, but between the pipes, it's still assuming that the pipe is liquid full between the stations. So, this is one of the areas where Waterhammer modeling and cavitation modeling can be tricky, is because you do have to do a lot of reading between the lines, where you have to understand what the simulation software is telling you and what's going on in reality, and then be able to connect the dots. So when we have vapor pressure, or when the vapor pressure is reached at a computation station, then that vapor volume begins to form. So the vapor pressure is going to be assigned as a new boundary condition at the station. So once cavitation starts to happen, the pressure at this station is going to be set to vapor pressure. At least that's if you're using the vapor cavity model. We'll talk a little bit more about that here in a little bit. And again, the normal, liquid flow is going to be between the stations inside the liquid volume. So again, you're just going to have to do some reading between the lines here. It's not too bad, and I'll show you how you can do that here later in the presentation. All right. Evaluating the output of cavitation in Impulse. This is just touching on some very basic ways to start evaluating your cavitation. So first off, when you finish running your analysis, one of the first things that you should take a look at is the transient maximum and minimum window of results. And right in here, you'll see a column that gives you the maximum vapor volume in each pipe. So here we have every single pipe listed, and it's going to tell you what the maximum vapor volume that grew to be was. It'll tell you which particular pipe station that happens at and the time that it reached the maximum value. So it reports the actual volume itself, and then it also will report the percentage of your section volume that has become vapor. So if you have a given pipe section that is this big, this column is telling you the percentage of that section volume that has grown to become vapor. So 30% right here would be vapor volume. That's going to be important here in a minute when we start talking about warnings and critical warnings that you might see when you are cavitating. When you start cavitating, you're not always going to see a warning message. You could very well be cavitating and have no warning messages at all. So that's why it's important to pay attention to these columns right here just to see if you have non-zero values. That means that you've got cavitation. And then depending on how much cavitation you have, then you start going down further rabbit holes. Another way to evaluate cavitation is by looking at the vapor volume at a given pipe station. So here, if you were to look at this particular pipe, you would see that the maximum percentage the vapor volume grows to be is 30%. So it looks like it happens at station 0, which is the inlet of that pipe. So you would look at the inlet of the pipe, and you can see how the vapor volume grows over time, and here's where it hits its maximum value. You can also do an animation for vapor volumes when you are doing profile plots. We'll take a look at that as well, but these are some places to start evaluating your cavitation. Is look at the transient max min table and then evaluating the vapor volume at a given pipe station. Okay, what is the difference between a warning message and a critical warning message? Well, in layman's terms, one is really bad and the other is really, really, really bad, right? Well, sometimes, but it's important whenever you see a warning message to read it, okay? Don't just blatantly ignore warning messages. You want to read them to understand what is going on. So when you're dealing with cavitation, there are two different types of warning messages that you can see. And so ultimately, as your vapor volumes grow and become larger and larger inside the pipe and inside the pipe section itself, the results are going to become more uncertain. Again, Impulse is assuming 100% liquid full pipes and constant wave speeds for your fluid. When cavitation happens, the wave speed changes due to the presence of vapor, and that's not accounted for in the method of characteristics. So pay attention to your vapor volumes. So here's a warning message that tells you that your vapor volume exceeds 10%. What this means is that if you have a given pipe station, okay, that pipe station represents a section that has a volume associated with it. What this is telling you is that the vapor volume in that section has grown to become greater than 10% of the section volume, but it's less than 100% of the liquid volume. So it's if this is your pipe right here, and let's say that this is 10%, and you're seeing, 11%, 30%, what that's meaning is that your vapor volume has grown to be larger than 10% of the liquid volume or of the section volume itself. That's where you see just a warning messages. Okay. Critical warning. A critical warning message is when your section volume for the vapor volume exceeds 100% of the liquid volume at the pipe section itself. So here, this is telling you that the vapor volume at a given section has grown to become 116% of the section volume itself. This just means that you have a very, very large vapor bubble that has grown. Okay, so again, the more that your vapor volumes become larger in size, the more uncertain that the results are. Now, let me ask you a question here. Does a 9 and 10% vapor volume differ significantly in terms of the uncertainty in results? How about 15% versus 95%? Okay, this is something to think about when you're evaluating these warning messages with your cavitating behavior. Okay, so are you going to see differences in uncertainty from 9 to 10% versus 15 to 95%? Well, it's all relative. So let's take a look at a very simple example here. Let's say that you have a 100-foot long section of pipe. And let's say that this actually extends much further. Let's say that you have, 1,000 or 2,000 feet of pipe. Well, if you have 2,000 or 1,000 feet of pipe, using 100-foot long sections is reasonable to start off with when you begin evaluating your results. Okay. Your model run times are dictated by the sectioning. So the more sections that you have in your pipe, the longer the runtime that you're going to be dealing with. And it's a massive increase in runtime when you put in more sections. So if the total pipeline is 2,000 feet long and you're doing sections of 100 feet in length, that's perfectly reasonable to start with. So if I have one section in 100 foot of piping, and I have a warning message that tells me the vapor volume gets to be 15% of the section volume, this is what we're looking at right here. So here is 15% of the entire section, and this has become vapor. Okay, that's where we see a warning message. Now, let's say that we take our pipeline and we've done our preliminary analysis, and now we want to get more resolution into our system. So instead of using 100-foot long sections in our 2,000-foot long pipe, we're going to use 10-foot sections. So we're going to change from 1 to 10 sections in that controlling pipe. So now if this 100-foot long pipe is made up of 10 sections, this is what we're dealing with. So it's the same pipe length that we saw before, 100 feet, but instead of breaking it in one chunk, we're breaking this 100 feet up into 10 chunks, okay? Now we get a critical warning message. And the critical warning message says, hey, your vapor volume is going to be 100% of the section volume. Oh man, a critical warning message just sounds really, really, really bad. Well, is it? Not necessarily. Just because you see the word critical versus not seeing the word critical does not necessarily mean that the world is going to fall apart, okay? Either way, you still have 15 feet of pipe length as vapor, okay? The only difference is that here it's less than one section, but here it's more than one section. But it's both the same amount of vapor volume. And so this is where, when you're looking at the word warning versus critical warning, and the advice of how the more that your section vapor volume grows, the more uncertain your results become. That is important to pay attention to, but it's also something that, don't just take it with a grain of salt, but just pay attention carefully to what you're dealing with. Are you looking at something that is, 100 feet in length versus 10 feet? Or are you looking at something that is 10 feet? If I double this and go to 20 sections, well, now I've got another section here, and, you can't stop there. But just don't get freaked out about seeing the warning messages. Okay, I'm just trying to illustrate what the difference in the warning messages mean on a physical basis. So here's an example, and I'm going to go over this example here in a little bit in Impulse itself. We have a very simple pipeline, and the pipeline is 2,000 feet long. And for me to actually get both warning messages, a critical warning versus a regular warning, usually I demonstrate this example with 20-inch diameter pipe instead of 12-inch. But I actually had to change the diameter to 12-inch to be able to get the warning message and the critical warning message based upon the sectioning I was using. So here, I'm closing the valve instantly within 1 millisecond right here, and we're going to see the difference in warning messages. So this is the situation where I'm using 100-foot long sections, okay? The total pipe length is 2,000 feet long, and I said, let's put 20 sections in there. That would give me each section being 100 feet long. So using that example here, this is giving me a percentage vapor volume of section volume of 20% at the outlet. And we can see that the vapor volume grows to be about 7.8 cubic feet, 20%, okay? Well, there's your warning message. If I was to change the sectioning to be 10-foot sections, so in the 2,000-foot long pipe, I'm doing 200 sections. This is where we now see our critical warning message. Very scary. This is telling you that you have almost 200% of section volume being filled up with vapor. Well, you still have the 7.5 cubic feet of vapor volume, and it's still happening at the outlet. So the point here is just to keep in mind your relative differences of section volumes. Okay, your vapor volumes are very similar, and when you look at the maximum pressure, 1308 versus 1500, yes, the results are different, and you have higher pressure here, but it's not significantly different. This might be, still not as bad. It just depends on the situation that you're dealing with. I want to again hit home things to keep in mind is that transient cavitation violates the method of characteristics assumption of liquid full pipes and constant wave speeds. So again, here's how the vapor volumes are tracked. Your pipes are going to remain liquid full, so each section between pipe stations is going to be liquid. The vapor that grows within a section is going to be remaining at a pipe station. So if this is what you're seeing in reality, where your vapor volume grows larger and larger in this direction, and then it starts to fizzle out, we're going to take this entire volume and we're just going to put it right there at the inlet. And then this amount of vapor volume, we're just going to put right here at this station. This teeny little bit, we're going to put right there. And then the volume in between with the calculations is still liquid densities. So this is what is happening behind the scenes. All right, so we're talking about vapor volumes there, and cavitation allows discontinuities in liquid flow rates. So this is something that's important to pay attention to. If you were to look at the mass flow rate at this particular pipe station right here, the mass flow rate coming into the pipe station is not going to equal the mass flow rate coming out of the pipe station. Okay, so this is another indicator that you have cavitation, is when you're looking at a particular pipe station, there's going to be an imbalance of flow at that particular pipe station. And the larger the imbalance in flow is going to indicate a larger vapor volume that's growing. So essentially, that imbalance in flow is simply your vapor volume integrated over time. And again, another assumption here is that your vapor volumes are remaining stationary in the model. So once we know that we're cavitating at these particular pipe stations, these bubbles are staying right where they're at. In reality, a vapor volume could potentially, one second. Excuse me. A vapor volume could potentially move up and down a pipe, especially if the piping is sloped, perhaps. So that can happen in reality. In the model, we're assuming that the vapor volumes are going to remain stationary. So keep that in mind as well. The more that you have cavitation in your system, those bubbles might be moving around more in reality, and we're not going to be tracking them. All right, now let's talk briefly about the two cavitation models that you can work with in AFT Impulse. There's the discrete vapor cavity model, DVCM, and there's the discrete gas cavity model, DGCM. So the discrete vapor cavity model, this is the default model of cavitation, okay? Either you're going to be cavitating when you hit vapor pressure. If your system is not at vapor pressure, you're not going to be cavitating. So in effect, you could uncheck this box to turn off cavitation. And if you don't have pressures that are at vapor pressure or below, your results are going to be exactly the same. There's no differences. So when your liquid is above vapor pressure, it's full liquid. Cavitation only happens when vapor pressure is reached. Once vapor pressure is reached, we're going to assign that station at vapor pressure. That means that the station is now a boundary condition, okay? When that pressure is a boundary condition, it's going to reflect pressure waves. So waves will not pass through a vapor cavity with the DVCM model, okay? It's going to only reflect them. So pipes upstream and downstream of wherever your vapor cavities are happening are going to be isolated from each other. So if I have a pipe right here, and here's a pipe station that's cavitating, I have stuff going on in here, and then other stuff going on over here, and they're not going to be talking to each other because there's this boundary right here set to vapor pressure. This can cause some major issues and some really significant noise with the vapor cavity model, as we will see. This is not very computationally intensive. It runs a little bit faster, but it can cause some major noise. And again, that's because the cavitation is only tracked at a pipe station. Now, the discrete gas cavity model is slightly different in its ability to handle cavitation a little bit better. It's a more advanced model. FYI, do not adjust these parameters, okay? Touching those parameters is a big no-no. Only adjust those parameters if you are specifically advised by AFT to do so. Otherwise, keep the defaults. I had a question come in. It's not AFT Phantom, it's AFT Fathom, by the way. And AFT Fathom does not predict cavitation. AFT Fathom can identify where cavitation happens. The way that it does that is AFT Fathom will compare your static pressure in the pipes to the vapor pressure. And if your static pressure is less than vapor pressure, it'll give you a warning message. So that means you're cavitating, but it doesn't model it. So it's a good question because Fathom can help you see where you might have a problem. All right, a little bit more about the DGCM here. One of the differences with the discrete gas cavity model is that this allows your system to become a little bit what I call squishy. That's because there's always going to be a small level of gas present inside the liquid, microscopic amounts of teeny little bubbles. And so as your pressure drops during a transient situation, that gas can expand. And so when this happens, this allows your pipe stations to interact a little bit better with the pressure waves. And so we're still assuming a constant wave speed, but it's just the nature of how the gas cavity model works. It doesn't change the wave speed when there's cavitation, but it has the ability to kind of mimic a modified wave speed behavior. And so the important thing to take away here is that, yes, it's more computationally intensive, but it allows pressure waves to actually have a level of not only just reflecting off of a pressure vapor volume, but it also allows some waves to transmit through a vapor volume with the gas cavity model. And that tends to smooth out the noise of cavitation behavior a lot more. So it is more advanced, a little bit more accurate, but it's also a lot more computationally intensive, a little bit longer run times, and results for the junctions are a lot more complex. Okay. The difference is the vapor cavity model does not start modeling cavitation until vapor pressure is actually reached. The gas cavity model will begin to allow some small amounts of vapor to grow before you actually hit vapor pressure. So when you're looking at that transient maximum and minimum table, like I showed you before, if you're using the DGCM model, they're not going to be zero anymore. They're going to be very, very small potentially, but they're not going to be zero. So pay attention to that. The impact on results here is that the vapor cavity model is going to create a lot more artificial waves in the system, and that just causes a lot of noise and it's hard to evaluate. And it can cause very large pressure spikes that may not be realistic. So the gas cavity model, it just handles this a lot better. All right, now I did provide the PDF of the presentation as a handout for you in the webinar. So you should be able to have access to that. If you are listening into the recording of the webinar, you're more than welcome to email me at the email address that I listed in the beginning of the webinar, and I'll be happy to send you the slides themselves if you're listening to the recording. So I'm going to breeze through these last couple of slides here a little bit more quickly, and we're going to start taking a look at Impulse itself. So just important thing to remember with the vapor cavity model, it sets a pipe station at vapor pressure. Waves do not transmit through that station in that case. They are reflected. The gas cavity model allows some level of transmission and reflection off of a vapor volume at a station. So the problem is that with the vapor cavity model, you can have waves that are pinging off the different pipe stations, and that's what creates the noise. All right, let's close the PowerPoint part of the presentation with some sage advice. Okay, it is better to fix the cavitation than to attempt to model the cavitation. I'm sure somebody said that quote somewhere. We always highly recommend that it is better to try and figure out how to solve the cavitating behavior. There are several ways rather than just to try and model the cavitation. All right. So fixing the problem is a lot better, and Impulse can help you with that. But in order to fix the cavitation, you do have to understand what's going on, and you have to understand what you're looking at. So with that, let's go ahead and take a look at AFT Impulse here. All right. So here's my situation where I modeled a 12-inch diameter pipe, and it's 2,000 feet long, and we're simply flowing downhill. We have a liquid surface elevation of 500 feet. Our pipe is at 470 feet, so we've got 30 feet of water above the location of where the pipe is connected. It flows downhill through this valve. The valve is initially fully open at a CV of 530, and then it exits right out into the atmosphere at 0 psig. And with the transient that I'm modeling here, we're going from a CV of 530 down to 0 in 1 millisecond. Very, very, very quickly. And so this is going to cause some major cavitation to happen. Now, again, I usually demonstrate this example with 20-inch diameter pipe. Okay, this is a 12-inch diameter pipe because when we break it down into the sectioning that's happening, I take that 2,000 foot long pipe and I'm putting 20 sections in there. So in that 2,000 foot long pipe, each section is going to be 100 feet long. So here, our time step is about 24 milliseconds. So the valve closure is happening faster than the time step. That means that the valve closure is in effect instantaneous. Okay. Now, I'm saving all of the interior pipe stations. So this is really important because if you want to look at what's going on inside of a pipe somewhere, not just at the inlet of the pipe or the outlet, it's important to include those stations in the output results. And I'm looking at what's going to happen in 10 seconds. And I'm going to start off by looking at the vapor cavity model. If you really wanted to be thorough, you could start with actually turning off cavitation and just see what happens. The reason why is because, well, let me show you. Here's the pressure at the valve inlet, okay? If you are evaluating cavitation from the get-go, you see a lot of chaotic behavior, and this can make it difficult to analyze your system right off the bat if you start seeing all this noise. So that's where one of the things that we advise is when you first run your model, keep it as simple as possible. You know, uncheck that box so that you're not modeling transient cavitation. For transient friction, either use simple or constant friction factors. That way you have a quick model runtime and you can get an idea of what's happening. And when you're not modeling that cavitation, you're not going to see all that noise, and it's going to give you just a good high level idea of what's happening. When you turn off cavitation, you will see negative absolute pressures. That is mathematically possible with the calculations. Not realistic, but that means that you've got cavitating results. All right. So keep that in mind. So that's a good place to start. But you don't have to. You could start off with being a little bit better than absolute basic. So you can start off using the vapor cavity model. That way, if you are cavitating, it will at least attempt to model it. All right, so I've got two scenarios, 20 pipe sections versus 200 pipe sections. So when we look at the results here, this is the warning message that I was telling you about. We have a warning, and it's telling us that we have 7.8 cubic feet of vapor volume. All right, and then we have 200 sections, and with the 200 sections, we have the same type of behavior here, where we've got lots of cavitation, but now we have the critical warning message. So when I'm evaluating cavitation, this is what I look at first. You know, when I'm doing, the only reason why I put in so many sections is because I have one pipe. All right. If I put a shorter pipe right here, where there's actually two pipes in the model, I'm not going to do 20 sections. Okay. When it's one pipe and it's 2,000 feet long, you can do 20 sections, and that's not going to mean anything for your runtime. So you can easily do that. So after I run my model, the first thing that I look at is warning messages, and I want to see, okay, what's the largest pressure that I see, and what's the maximum vapor volume, and when does it happen? Here it happens at about 5.5 seconds, and that vapor volume grows in about 2.5 seconds. So this is where I just start to get a feel for what's going on. It's important to point out that this does not tell you the whole story, so don't stop there. You got to dig deeper. Here's what I usually do next. Something that's really cool is that you can actually start by generating graphs right from the workspace. So if I click on this valve, I can right click and I can say, show me what the transient valve CV is versus time. Well, this isn't really exciting. This is doing exactly what I told it to do. It's closing instantly in 1 millisecond, and so it's just a good sanity check to see to make sure it's doing what you told it. So that's a good thing to do. You can look at other junction results. If I had put a CV versus open percentage curve, I could look at the open percent versus time as well. You can also generate a graph for the immediately connected pipes. There's only one pipe connected here, so it's only going to look at the inlet of the valve. So I'm going to start by looking at pressure. All right. Now, when we have our valve closure, This is the instantaneous surge pressure that can be approximated with the Joukowsky equation. All right. So when we take that fluid velocity, the steady state fluid velocity is 18 feet per second. All right. It's a high velocity. Well, that's going to generate a really high surge pressure when you close that valve really quick. So we've got an initial pressure surge of about 1200 psia. Now, you do have a little bit of line packing as the pressure from the valve reflects and moves upstream, and then it drops. And then it starts causing all this madness. Well, understanding what's going on at the valve itself can be difficult if that's the only thing that you're looking at. The next thing to do would be to add in the vapor volume itself. So if I add a second parameter and I change this parameter to vapor volume, this gives a little bit more clarity as to what's going on. So here we see that the pressure at the valve hits vapor pressure and it stays at vapor pressure for a long time. This is when that vapor volume grows and it becomes nice and big, and then it starts to do the opposite of growing. I guess shrinking is the right word. And then once it hits zero, think of that as a balloon popping. Once this balloon pops right here, at this time, you're going to see an associated pressure spike. And bam, you do. It jumps from vapor pressure up to almost 700 psi in one time step. And then as we go back to looking at the graph, then we see some smaller vapor bubbles, and we see associated pressure spikes, and then we see a larger vapor bubble after this pressure spike up here, and we see a whole bunch of madness. Now, after we're looking at the immediate station upstream of the valve, what we want to see is what is going on throughout the pipe itself. So that's what we're going to do a profile plot. So if I open up another graph tab here and I do a profile plot, I might start by looking at the steady state value compared to the maximum and minimum pressures. All right, so here we see that at the valve, here's the valve right here. This is the initial pressure in the steady state. Here's the maximum pressure. Here's the minimum pressure. Well, look at this. Right off the bat, you see that this is really bad because the entire pipeline hits vapor pressure at some point. Okay. Just looking at the maximum and minimum value is not enough. This is where using an animation is incredibly helpful. This is another reason why I like to save the intermediate stations in the output file. So again, if I go back to it right here, and when I look at the output pipe stations, when I look at the output pipe stations right here, I want to make sure that this says all stations. The reason why is because when I do, I can use this option instead of this option. Now, that will cause your model to run for a little bit longer of a runtime when you run your model, but it gives you the ability to do this. When I play the animation, oh, that looks like it's going really super fast. Look how quickly that pressure jumps up. Well, the magical thing I can do is I can pause the animation, and then I can use the time scale bar right here, and I can back up time steps one time step at a time. That way I can see when things go crazy, I can slow it down and I can move forward one time step at a time. So this is when the valve instantly closes, and then we see this pressure wave starting to pass back through the system. If you are not using the output option, you cannot do this by pausing and moving backwards. If you're doing the solver, you can't do that. So make sure you save your stations initially. That way you can use the output option. It's a lot easier to evaluate your results. So here's what's happening. That valve slams shut, our pressure surge increases, and it's traveling up the pipeline, okay? This is just basic Waterhammer stuff. Nothing is cavitating yet, okay? Once I get all the way to the reservoir is a fixed pressure that's going to reflect the wave. And so now it's reflecting the wave back to the valve. This is one wave cycle. Now, the valve is closed, so at this point, the valve is going to, or the pressure is going to now reflect negatively. So this is where low pressure surges are just as bad as high pressure surges, because now when it reflects at vapor pressure, and now that starts moving upstream as well. Everything starts to hit vapor pressure, and as the pressure wave oscillates, if I slow this down, now we start to see cavitating behavior. So there's a lot of chaos going on with this cavitating results, and we start to see a lot of noise. Okay, now, because I'm only using the discrete vapor cavity model, I'm not going to try and fully understand and evaluate these results because there is so much cavitation going on. Okay, this is just important to teach you how to start looking at your cavitating results. So when you start looking at the valve itself and you see all this happening, that's because of all the cavitation that's going on inside the piping. So when you first start evaluating the results, spend a little bit of time looking at this. Do your animation of your pressure. We can also add in an animation of the vapor volume as well. I'm going to turn off a lot of these other graphs. And so when we play this, see there's no vapor volumes down here yet. But once we start to cavitate, you'll be able to see now we've got some vapor volumes that are growing all throughout the pipeline. Okay, and so there's a whole bunch of cavitating behavior, and it starts popcorning, and the results get to be pretty noisy. Okay, so the key thing is we don't really care to pay that much attention to those types of results. The main thing is, what is the maximum pressure that I'm getting? What's the relative magnitude? I'm looking at the relative magnitude of these pressures. I'm seeing what this pressure looks like. When does that happen? But now let's compare this to if I'm using 200 sections in the pipe. So this would be the next thing that you might want to do in your analysis is, I know that I've gone over an hour, and just like usual, if you have to head out of the webinar, no problem there. You will be sent a link to the webinar recording later this week or early next week, and you can watch the remainder of it at your leisure, or you can stick with me today. No problem either way. All right, so here I'm now using 200 sections in the pipe. So now instead of 100-foot sections, I've got 10-foot sections, okay? Now, this does increase the runtime. It says 8 minutes, but it actually wasn't really that long. Here are my results. There's my scary critical warning message that we talked about. We also see cavitation happening in many other areas, and we can see that we do have a higher pressure surge. So let's look at some graphs. What's happening at the valve? Let's start here first. So I'll plot the pressure at the valve. And here we can see that there's a lot more noise going on. Well, this makes sense because I'm using really short sections, so we're going to see a lot more noise because of those waves reflecting off the various stations much more quickly, and the pressure values get to be a lot higher. Well, this is really powerful is because you can compare this to the other scenario using multi-scenario graphing. So when I turn on the other scenario, this is what I'm looking at. So here is, if I'm using 20 sections in the controlling pipe, here's what it looks like if I do 200. Okay, so this is 20, 200, 20, 200. So the pressures here are about the same. When you look at those peaks for red and blue, they're very similar. And then when you compare these maximum results with these maximum results, they're also relatively similar in magnitude. Okay. Now, again, you don't really need to pay too much attention at trying to dive deeper to this, because your next step is to try using a different cavitation model. So here what I'm going to do is I'm going to insert a new scenario. And I'm going to rename my original scenario called DVCM for the discrete vapor cavity model. Now what I'm going to do is I'm going to right click on this parent. I'm going to say clone with children. And we're going to call it DGCM for discrete gas cavity model. So the discrete gas cavity model, the only thing I'm going to change is looking at the discrete gas cavity model here. Again, don't touch these other parameters, just keep them the default. Click OK. And let's check to make sure that that propagated down to this other scenario. So we've got discrete gas cavity model here, which is good. And then discrete gas cavity model here as well. That's good. And so now we'll do a batch run of those two scenarios. This is how you dive down the rabbit hole. You start off looking at things in a real basic sense, maybe add some more pipe sections to get a little bit more resolution in the data to see what's going on, and then use the other cavitation model. Okay, so here we see similar stuff. So if I'm looking at the 20 sections, we can see a similar vapor volume that grows, and the pressure spike is similar to what it was before. Here's the 200 sections example, but we want to look at graphs. So I'm going to go to my graph results window here, and I'm going to look at the outlet of the pipe. This is the 200 sections example. Let's go ahead and compare it to the other scenarios. So I'm looking at all four scenarios, and things look pretty crazy here. So it's helpful to uncheck the boxes to turn off all of those different options. So again, 20 sections with the discrete vapor cavity model. Here's 20 sections with the gas cavity model. So you can see how simply switching from the vapor cavity model to the gas cavity model, it starts to smooth out results a little bit more. You do see bigger spikes with the vapor cavity model and than you do with the gas cavity model. So the gas cavity model, this is going to be more reliable. Here you see really large spikes. It's uncertain if those are actually accurate or not. Okay, but here, this is what we want to be concerned about. What are those magnitudes looking like? Now let's look at the 200 sections. So here's 200 sections with the vapor cavity model. Here's 200 sections with the gas cavity model. So if I toggle the vapor cavity model on and off, you can see how it's much, much more noisy than the gas cavity model situation. Okay, so ultimately, whenever you're dealing with the vapor cavity model, you're going to see a lot more noise. And here, this is just where you're trying to get a feel for, what are my magnitudes? This is a high magnitude here. Is it similar to what I'm seeing here? That will give you some more confidence in those results that you're seeing. Let's see. Another quick question that came in. If we already have a Fathom model and we want to evaluate cavitation and impulse, what's the best way to do this? Simply import your model from Fathom into AFT Impulse, then do your transient analysis, and then you'll be able to evaluate your cavitation. Good questioner. You can easily open your Fathom model in Impulse, no problem. That's the beauty of AFT software. Now, for this particular situation, when I'm looking at my scenario tree, I could take this a little bit further where I take my discrete gas cavity scenario, the parent and the two children, and the next thing that you could do is in the analysis setup is under transient friction, change this to using the advanced unsteady Brunin option. This actually does a really good job. This has a tendency to really smooth out the transient results themselves. Okay, so this could be another layer of analysis to do some more comparisons. Again, what you're doing is you're comparing all of these scenarios to each other to see what are my magnitudes of maximum pressures. Are they around the same value? Are they happening in the same areas, the same time steps? Am I seeing them happen with both cavitation models? Am I seeing them both when I change sectioning? Am I seeing them when I use unsteady Brunin? When you start to see those results become similar in all those different cases, that's what will help give you more confidence on if those results are realistic. But rule number one, again, is don't cavitate. Fix the cavitation. So at this point here, I'm doing a very fast valve closure. It's a 12-inch diameter pipe, and I'm closing the valve in 1 millisecond. Most likely, it's going to take a little bit more time for that valve to close. So I'm not going to try and deal with evaluating the cavitation any further. I'm going to try and stop cavitation. So I'm going to try and call this longer valve closure. All right, so my longer valve closure scenario, this is still using 20 sections. That's fine. It's got the gas cavity model, but this time, instead of closing in 1 millisecond, I'm going to close this in 2 seconds. Very simple change. So if I close this in 2 seconds, wow, I don't see big red scary warning messages anymore. That's good. Now, you do still have non-zero vapor volume because that's going to be the case when you're dealing with the gas cavity model. So there is some cavitation, but not as much. Well, let's see how much. Let's right-click on that guy and generate a pressure plot. Wow, this is much better. Look at the difference in results here. if I'm looking at pressure and vapor volume, in this case, we only hit vapor pressure once. That vapor volume grows. It's not very large. Remember the percentages. This is 0.06% of that section volume. Section volume is 100 feet long, so that's 0.06% in that case. So here we're seeing much better behavior simply by closing the valve in 2 seconds instead of 1 millisecond. So already you're in a much better situation. Now let's try that advanced Brunun equation situation. Brunun for unsteady friction. And let's see if this helps smooth things out a little bit more. And we'll be able to see what the impact looks like. So again, the sage advice, remember, it's better to fix the cavitation rather than trying to model the cavitation. So if I look at that same area for pressure for both the scenarios, well, they're very similar to each other. And so this gives me good confidence as to what's happening. Well, if I was able to eliminate cavitation or the majority of it simply by closing the valve within 2 seconds instead of 1 second, another thing that you can try doing is the 80-20 rule. This is the last thing I'm going to show you today. So not just closing a valve slow or closing a valve slower is better, but that's not the only thing that can help. Let's say I still want to take 2 seconds to close the valve, but instead of going straight from 530 to 0, I'm going to go from, let's see, what is 530 times 20%. So I'm going to close this. So I'm going to close this a huge amount really, really quickly, and then the rest of the way a lot more gradually. This does a phenomenal job at mitigating surge simply by the way that you close the valve. So let's see if this eliminates the cavitation entirely. So when I run the model, take a look at our results. Vapor volume, well, I guess sometimes it makes things worse. It depends on what type of valve that you have, and this is a whole other rabbit hole to go down. So here we do see a much higher pressure than we saw before. If I look at all those 3 scenarios, so this is a bad example. In general, closing the way that you close the valve is just as much, if not more important than simply closing the valve slower. If you go to our website for Purple Mountain Technology Group, you can read our blog. And if you go to our blog page here on pmtechgroup.com, I wrote a blog article a while back stated, just close the valve slower, right? Well, you might think, if I just close the valve over a slower period of time, will that mitigate surge? And this is an article that demonstrates that that's not always the case. So this will introduce you to some more of those concepts. Okay, so this is our webinar today on evaluating cavitation. I hope that it gave you a good idea of what cavitation is, how to evaluate it, how to use AFT Impulse to understand the cavitation, and then a couple of things that you can do to eliminate cavitation. The way that we reduced it massively simply changing the valve closure, 1 millisecond to 2 seconds. That did a really good job. Another thing you could do is change the diameter of the pipe itself. Well, if I increase the diameter, that's going to reduce the steady state velocity. When you reduce the steady state velocity, that's going to decrease the sudden pressure surge when you close the valve. So that's another technique that you can do. And then you could try the 80-20 rule. That does work a lot of the time. Not always. It depends on what kind of valve you are using, and it depends on what kind of system that you're using it in. But again, this should hopefully give you a better idea of how to understand cavitation with AFT Impulse and how to get around it. And if you have any questions, please feel free to get in touch with us and let us know. If you'd like for us to help you with any of your projects, maybe you're limited to time, feel free to please reach out to us and we'll be glad to assist. Thank you all very much for listening in today, and we hope that you all have a wonderful rest of your week.